And then we start with proving 4.52. As I said, the point is that you see in this proof a little bit how the use of a basis allows you to move every problem to Rn. So, so we show 4.52, and there were part A and B. So we start with part A. So again, maybe I should write it one more time. V is a vector space. And let's call it B, B for basis, V1 to Vn, a basis of V. And now we take S, a subset of V, with m elements, and m is larger than n. And what we need to show, then this set is linearly dependent. So if you have too many elements, there must be some linearly dependency in there. No? So S linearly dependent. Okay, and now you see actually how difficult this is. No? Also, we don't know what the vector space is. We don't know what the basis is. I mean, these might be functions actually, like sine and cosine functions. We have no clue. I mean, everything is here very, very general. But it turns out to solve this problem, we can rely on the results from chapter 1. And the secret to this is the existence of a basis. Okay, so how do we do this? So first, what do we need to show that's linearly dependent?
Hi, Professor.
Yes?
I'm not able to hear anything.
Oh. Also I hear you. Anyone else doesn't hear me?
I can hear you, Professor.
I can hear you just fine.
Huh. Can you check your setup? Also, because I have not changed anything.
I found it. Thank you.
So you hear me again?
Yeah.
Okay, so very good. Thank you. Yeah, that's always scary if suddenly things disappear. Okay. Okay. So how do we show linearly dependent? That means we have to find non-zero coefficients, let's say C1 to Cm, such that C1W1 plus C2W up to CMWM is equal to 0. So to find non-zero coefficients C1 to Cm such that C1W1, C2W2 plus CMWM M is equal to 0. This is a zero vector. No? Okay, and again, you see how in the world would we do this? We don't even know what these things are. No? Okay, and the starting point is we put in our basis. Because this is a basis, every vector has coordinates. Every Wj has coordinates. And so let's call, now we are a little bit in an index trouble. Like that's actually the trouble always linear algebra. You have always these indices and double indices like in a matrix, and that's happening here too. So the price you pay for linear algebra, you have to live with indices, no? Okay, so let's call the coordinates from Wj. We call them A1j up to ANJ. N because our basis has n elements. So that means Wj is the linear combination. Let's take here the index k. K goes from 1 to n. A, kj, vj. Because this is a basis, so every vector can be written with half of the basis, especially our w vectors. And these coordinates, even better, they're unique. They exist and there's nothing else. Okay, now this equation can be written now with the help of the basis vectors. So let's call this star again. So the point is I don't like to copy it. So star is equivalent, or I just write it down in a short way, 0 is equal to this, and now I write it also as a sum symbol. So now for every wj, I use this formula. But now, so sorry, this is actually k here, no? Not j. Because we have to use always all the bases. I was just wondering, that's weird. Okay. wk, no? Because we have to use all basis vectors for every vector wj. Now we switch the summation. We can do this because this is finite, not in like in calculus 2 where you have infinite summation and you have to be careful. Here everything is just finite. So we just distribute this around. So I say this is k goes from 1 to n. Then I can actually vector the vk, and what's inside, all the rest. Yeah, so cj times akj, and I just switch these are just numbers. Okay, but now vk is a basis. So how can you make a basis combination equal to 0? Only if every coefficient is 0. If and only if. So now this is if and only if, because our B is a basis. If sum j goes from 1 to m, akj, cj is equal to 0, for k goes from 1 to n, for all the basis vectors v1 to vn. But now we see, oh, so what happens? So this is so abstract. We don't even know what the 0 is. It might be a 0 function, a 0 matrix, a 0 vector. We have no clue. But by using a basis, suddenly we have a linear equation system. So the basis took the abstract problem and turned it into a linear equation problem. So now we see, oh, this is just equivalent to the following. We have a11 to a1m times c1 to cn equal to 0, 0. And I should write it like this. No, okay. I write it like this. So here the last one would be an1 to an m. So this is our coefficient vector. This is the 0 vector. And how big is this matrix? It's n cross m with m larger than n, no? Because we have more vectors than the basis has. Now the question is, can we find non-zero coefficients that solve the system? So can you find non-trivial solution to this? And now we see, oh, that's something we actually learned in chapter 1.2. If you have a rectangular matrix with more columns than rows equal to 0, you always find solutions that are not all zeros, the non-trivial solutions. And again, the reason was very basic. If you do reduced row echelon form, if everything has leading ones, there are still some columns left where you have parameters. So that comes down to the old reason. So therefore, that was theorem 1.22. There are non-zero solutions. Actually, there are infinitely many C1 to Zn. And that implies that this is linearly independent. So here you see kind of the power between the idea of a basis. Basis in a vector space reduces every linear problem in the vector space to a linear equation problem. And the idea is linear equations, we can always use reduced row echelon. Okay, so that shows part A. Part B, we have the same assumption, A a vector space, V a vector space, B a basis. We start with a set, but this time we have less than n elements, and we have to show it doesn't span the vector space V. Even we don't really know what V is, actually, turns out, but it turns out we don't need this because we have a basis. And this time it's not so convenient that we have theorem 1.22. We should have done this also, but the book doesn't have it, so I also didn't do it. But it's a similar argument, and you will see this time we will end up with a linear equation system with more columns, more rows than columns. Okay, otherwise everything is the same. So especially I also will use this relationship here that every vector can be written with the help of the basis, but I will write it again. Okay, so we go to part B. So part B is we have now a set S of V1 to Vm. This time we have less than n vectors, so less than the number of elements in the basis. And to show is that the span of S is not equal to the whole vector space. So essentially it means we can pick a vector u, no matter what you do with these guys, you cannot reach u. So that means to show there is a u in V such that C1 V1 plus Cm, no, sorry, this is actually W. Sorry. These are the W's. The V's are our bases. It's not equal to U, no matter which coefficients you pick. No? So no matter what you pick, you can never get U. So we have to show this U exists. Is there a U such? And again, that by itself is a very complicated problem. I mean, again, because we all don't know what vector space we have, we don't know what these things are. But the only help we have is a basis. No? So the vector u and every w can be written with the help of the basis, because that's the definition of a basis. The basis spans the whole vector space. So again, B basis implies u is a combination of the basis vectors. Let's say k goes from 1 to n, that's the number of basis vectors. Let's say call the coefficients dk, vk, and every w, that's the same as before. So wj is also equal to k goes from 1 to n, akj, wk. So now, if we set this equal, remember we like to show it's impossible that's equal, but let's set it equal first. So u equal to c1 w1 up to cm wm is equivalent to left and right. I put in my basis. So u is sum k goes from 1 to n dk vk. And here I plug in some j goes from 1 to m cj wj. That's this here written again. Now I use this one here. So this is sum j goes from 1 to m cj, then sum k goes from 1 to n akj vk. And again, we can actually flip. So that's the same argument as before. We flip the two sums. So we have k goes from 1 to n. Now we make big parentheses. We have taken out the basis vectors, and inside is all the rest, which is sum j goes from 1 to m akj cj. And now again, we use the fact that the V's are basis. So if the same vector can be written in two different ways, the coefficients must be the same, because what we learned in the last section, the coordinates are unique. So this is a coordinate and this is a coordinate, they have to be the same. So this implies, because B is a basis, that we have the following equation system. This has to be equal to this for all k. So sum j goes from 1 to m, akj cj is equal to dk for all k. K goes from 1 to n. Again, we can write this as a linear equation system. So here is a11 to a1m, and the last row would be an1 to anm, multiplied by c1 to, no, sorry, yeah, no, that's correct, c1 to cm equal to d1 to dn. And I think I did the picture correct. So m is smaller than n, so our matrix is actually longer, also more rows than columns. And again, come back to our question, what do we actually like to show? We like to show that there are D's, so it means there are U's where you cannot solve the system, no? The point is we like to show it's not always possible, no? Yeah. Okay, and why is it possible to do this? Why can I find actually coefficients D such that we cannot solve this system? Okay, the thing is we have here more columns than rows. So if we bring this side to reduce to echelon form, it will stop somewhere here, and then we have 0 rows here. And whenever there's a 0, I put a D which is non-zero, and that makes it impossible to solve. So we can find a vector d1 to dn such that this is impossible to solve. Okay, and that means we can find a u such no matter how you pick the coefficients, you will never reach the u. And the u is given by a linear combination of the v's. So this is a linear equation system where we can always find a right-hand side where you cannot solve it. And it leads to the fact that this vector space v, whatever it is, has a vector u that cannot be written as a linear combination of the w vectors. And that finishes the proof of part B. So it means span of S is impossible to be equal to V. It's smaller, yeah, like a plane in R3 or R3 in an R4. So we have a smaller result here. Okay, so like I said, this is a little bit more abstract, but, and like I said, also there's actually very few homework for this section. Nevertheless, the result we get is really, really important. It says, if you have a vector space with n elements, let's say a vector space with a basis of 4 elements, you cannot find another basis with 5 elements. If a vector space has a basis with 4, it's always 4. And now the usual thing in mathematics, if there's one number which is always not, which is kind of given for a certain structure, this number gets a name. And also very fittingly, actually, this number, which tells you the number of elements in a basis, is called the dimension of a vector space. So if we say a vector space has dimension 4, it means every basis has 4 elements. Yeah. Okay, so this is the next definition. And then we do some examples. Most of them are just straightforward. Only one will include